Gravity is so familiar that we rarely question it. It holds your body upright, keeps the oceans from drifting away, and guides the planets in their endless motion. It feels obvious, predictable, almost boring. And that is precisely why it hides its true nature so well. This journey begins with what seems ordinary and slowly unravels it. We start with gravity as humans first encountered it, not as an explanation, but as a pattern, a rule that worked long before anyone knew why. From falling stones to wandering planets, gravity revealed itself through repetition, not understanding. As measurements grew sharper, that comfortable picture began to crack. Gravity refused to behave like other forces. It could not be blocked, weakened, or switched off. Everything fell the same way. Light bent, clocks drifted apart, motion changed even when nothing appeared to act. The deeper we looked, the less gravity resembled a pull, and the more it resembled something woven into the structure of reality itself. Along the way, space and time stop being passive backgrounds and begin acting like physical participants. Free fall becomes natural, weight becomes an interruption, acceleration and gravity blur into the same experience. What once felt like force begins to look like geometry, not as an abstract idea, but as something clocks and light can directly measure. We follow this evidence outward, from everyday motion to orbiting worlds, from black holes where gravity is strongest, to the expansion of the universe itself. At every scale, gravity tells the same story. Not of attraction, but of structure. Not of pulling, but of paths shaped by space-time. And then we reach the edge. The places where geometry itself stops answering questions, where singularities appear, where quantum uncertainty takes over, where physics, for the first time, stops not because it failed, but because evidence has not yet arrived. This is not a story about solving gravity once and for all. It is a story about how far careful observation can take us, and where honesty demands we stop. About how something can be described with extraordinary precision and still remain fundamentally unexplained. By the end, gravity will feel less familiar than when we began, but it will feel more truthful. Not an illusion of nature, but a reflection of how reality reveals itself, layer by layer, always exact, always incomplete, and always stranger than intuition expects. With that in mind, let us jump straight into the universe, where gravity was measured long before it was understood. Gravity is one of the first regularities every human encounters, long before it is ever named or questioned. An object released from the hand moves toward the ground. A thrown stone slows, pauses, and returns. Rain falls. Rivers flow downhill. None of this initially feels mysterious. It feels inevitable, so reliable that it disappears into the background of experience. Gravity presents itself not as a puzzle, but as part of how the world simply behaves. For most of human history, gravity was never studied as a problem. It was lived with. People built shelters that stayed on the ground. They learned how weight strained muscles and how height made falling dangerous. These lessons required no theory, only repetition. Gravity was known through habit, not through explanation. It shaped daily life without ever demanding to be understood. When early thinkers did attempt to explain why things fall, their explanations were guided by intuition rather than measurement. Objects were said to move toward their natural place. Heavy things belong closer to the Earth, lighter things farther away. These ideas felt reasonable because they mirrored experience, but they did not allow prediction beyond what was already obvious. They could not tell how fast something would fall, or how motion would change under different conditions. They described appearances without testing them. The transformation began when gravity was approached not as a tendency or purpose, but as a measurable pattern. This shift did not require knowing what gravity was. It required only that its effects be consistent enough to quantify. How far does an object fall in a given time? How does motion repeat? How do paths curve when objects move sideways instead of straight down? Measurement turned familiarity into data. At the same time, the motion of the planets revealed a deeper reach of the same phenomenon. The lights wandering across the night sky were not wandering at all. They followed precise paths that repeated over years and decades. These paths could be described mathematically with astonishing accuracy. Whatever caused objects to fall toward the Earth also governed the motion of the Moon and the planets. Gravity was not local. It extended across the solar system. The achievement of classical gravity was not the discovery of its nature, but the discovery of its rule. A mathematical relationship connected mass, distance, and motion. According to this rule, every mass influences every other mass. The strength of that influence depends on how much mass is involved and how far apart the objects are. As distance increases, the influence weakens in a precise and predictable way. The power of this description lay entirely in its success. Using it, astronomers predicted planetary positions centuries in advance. Engineers calculated trajectories. Navigators crossed oceans guided by celestial mechanics. The agreement between calculation and observation was so exact that it inspired deep confidence. Gravity behaved as though the rule were true everywhere it could be tested. Yet this success concealed a limitation. The rule described what happens, not how it happens. It offered no account of how one object affects another across empty space. There was no description of a signal, no medium, no delay. The influence appeared to be immediate. If one mass moved, the other responded without waiting. This was not presented as a physical explanation, but it remained an unavoidable implication of the mathematics. Even the architect of the rule recognized this unease. A law that works does not automatically explain. The calculations could be trusted, but the underlying picture of reality remained incomplete. Gravity acted, but the mechanism of its action was left undefined. This ambiguity persisted because nothing yet forced it to the surface. Within everyday experience and even planetary scales, the predictions remained accurate. Space was treated as an empty stage. Time flowed uniformly, the same everywhere. These assumptions were not proven. They were accepted because they worked. What distinguished gravity from other interactions was its universality. Every object responded to it in exactly the same way. Composition did not matter. Structure did not matter. A stone and a feather accelerate identically when air resistance is removed. Gravity did not discriminate. It acted on everything that had mass, without exception. This universality was measured long before it was explained. It hinted that gravity was unlike any ordinary force. It behaved less like a push or pull, and more like a property of motion itself. But at this stage, it remained only a hint. Gravity stood as a profoundly successful description, rooted in observation and calculation, precise in its predictions, and silent about its deeper meaning. The quiet strangeness of gravity became clearer as experiments grew more precise. When objects of different composition were compared, their behavior under gravity remained identical within the limits of measurement. Wood, metal, stone, and glass all accelerated toward the Earth at the same rate when other effects were removed. This was not an approximation. It was a repeatable fact. Gravity did not care what an object was made of, only that it existed and possessed mass. This feature set gravity apart from every other known interaction. Electrical forces act only on charged objects. Magnetic forces depend on orientation and motion. Chemical forces depend on structure and bonding. Gravity alone treated all matter equally. No experiment ever revealed a material that fell faster or slower because of its internal composition. The effect was universal, and universality in physics is rarely accidental. At the same time, gravity displayed another unusual property. It could not be screened or blocked. No wall, no material barrier, no arrangement of matter could shield one object from the gravitational influence of another. The Earth pulls on everything above its surface, regardless of what lies in between. Gravity passed through rock, metal, and vacuum without attenuation. It behaved as though space itself offered no resistance to its influence. These properties made gravity difficult to picture as a conventional force. Forces are usually mediated by something. Sound travels through air. Water waves move through liquid. Even light, though it requires no material medium, propagates at a finite speed. Gravity, as it was described, seemed to ignore these patterns. Its influence appeared everywhere at once, without delay and without a carrier. For a long time, this discomfort was tolerated because no observation contradicted the predictions. As long as gravity worked, the lack of mechanism could be overlooked. But physics does not stand still. New theories were emerging that treated space and time themselves as measurable entities. The behavior of light revealed that time did not flow the same for all observers. Distances were not absolute. Motion affected measurement in ways that classical physics could not accommodate. These developments created a growing tension. The classical picture of gravity assumed an absolute space and a universal time. Yet experiments involving light showed that such absolutes did not exist. The speed of light remained the same for all observers, regardless of their motion. To preserve this fact, space and time had to adjust. Lengths contracted. Clocks ticked at different rates. These were not philosophical ideas, they were measured effects. Within this new framework, the idea of instantaneous gravitational influence became increasingly problematic. If nothing could travel faster than light, then gravity could not act everywhere at once. Either the law of gravity was incomplete, or the underlying assumptions about space and time had to be reconsidered. The success of classical gravity was no longer enough. Its internal consistency was now in question. This did not mean that the old calculations suddenly failed. Planets continued to follow their paths. Apples continued to fall. But the deeper picture had begun to crack. Gravity had been treated as a force acting within space and time. The emerging evidence suggested that space and time themselves were active participants in physical processes. The universality of gravity now appeared in a new light. If all objects fall the same way, regardless of their composition, then gravity might not be a force in the usual sense at all. It might instead reflect something about how motion occurs in the presence of mass. This was not yet a conclusion. It was a question that had become impossible to ignore. Gravity remained an observed phenomenon, precisely measured and deeply trusted, but the foundation beneath it was shifting. The patterns were clear. The predictions were accurate. Yet the framework used to describe them was approaching the limits of what it could consistently support. The growing strain between gravity and the emerging understanding of space and time did not announce itself loudly. It appeared quietly in the margins of theory, in questions that refused to stay settled. If space and time were not fixed backgrounds, then treating gravity as a force acting within them began to look increasingly artificial. The mathematics still worked, but the picture they implied no longer matched what experiments were revealing about the structure of reality. One of the most telling clues lay in the relationship between motion and gravity. An object in free fall does not feel heavy. This is not an abstract statement. It is something that can be experienced directly. Inside a freely falling elevator, objects released from the hand float alongside the observer. There is no sensation of being pulled downward. Weight disappears, not because gravity has vanished, but because everything is falling together. The motion feels inertial, indistinguishable from drifting through empty space. This observation was subtle but profound. Forces are usually felt. They produce strain, pressure, resistance. Gravity, in free fall, produces none of these sensations. The experience of weight arises only when motion is prevented, when the ground pushes upward and interrupts the natural path of motion. Gravity itself leaves no local trace. It guides motion without announcing its presence. The same behavior appears on larger scales. Astronauts orbiting Earth are not beyond gravity. They are deep within it. The Earth is pulling on them continuously. Yet they float, they drift, they experience weightlessness not because gravity is absent, but because they are in uninterrupted freefall around the planet. Gravity is acting, but it is not felt as a force in the usual sense. This created a conceptual divide. On one hand, gravity was described mathematically as a force. On the other, its effects looked indistinguishable from inertia. Objects moved as though they were simply following the natural paths available to them. The distinction between falling and coasting began to blur. At the same time, gravity resisted every attempt to assign it a conventional physical carrier. There was no known particle that transmitted it. There was no detectable medium it traveled through. Unlike light, it did not scatter or weaken when passing through matter. Its influence depended only on mass and distance, not on what lay between. None of this invalidated the classical law. Its predictions remained astonishingly accurate. But accuracy alone was no longer enough. Physics had reached a stage where internal consistency mattered as much as numerical success. A theory that worked but conflicted with deeper principles could not remain untouched forever. Gravity now stood in a peculiar position. It was universal, precise, and indispensable. Yet it fit awkwardly within the emerging picture of a universe where space and time were flexible, dynamic, and observer-dependent. The force-based description captured the pattern, but it no longer felt fundamental. By the early 20th century, gravity had been measured to extraordinary precision and tested across vast distances. It had proven itself as an empirical regularity beyond any reasonable doubt. But its true character remained unresolved. Gravity was known through what it did, not through what it was. It shaped motion everywhere, yet left behind no clear mechanism. This unresolved tension marked the end of gravity as merely an observed rule and the beginning of gravity as a deeper question. The stage was set for a radical shift, not driven by philosophy or speculation, but by the demand that nature's most reliable patterns be described in a way that was consistent with everything else that had been measured. The classical description of gravity had earned deep trust through its success, but success can mask fragility. A theory may work perfectly within familiar conditions while quietly relying on assumptions that fail beyond them. As physics advanced into new regimes of speed, precision, and scale, gravity began to expose exactly this kind of hidden weakness. It was not that the predictions suddenly failed in everyday life. It was that the conceptual foundation beneath those predictions could no longer remain untouched. At the heart of the classical picture was the idea that gravity is a force acting between masses across space. This framing felt natural because it mirrored how other interactions were understood. Objects pull on each other. The stronger the masses, the stronger the pull. The farther apart they are, the weaker it becomes. This language was effective, but it carried an implication that had never been tested directly. It implied that gravity exerted influence across distance without delay. In a universe where time was assumed to flow identically everywhere, this posed no immediate contradiction. If time is universal and absolute, then instantaneous influence raises no alarm. But experiments involving light revealed something deeply unsettling. Time does not behave this way. Events that appear simultaneous to one observer are not simultaneous to another. Motion alters the flow of time itself. This was not interpretation. It was measurement. Once time lost its absolute status, instantaneous action became a problem. If gravity acted immediately across distance, then it would violate the same causal structure that governs every other known process. Effects would occur without waiting for causes to arrive. The universe would contain a privileged signal that ignored the fundamental limits imposed by the speed of light. No experiment supported the existence of such an exception. This tension was not philosophical, it was practical. If gravity propagated instantly, then changes in the distribution of mass would be felt everywhere at once. If the sun were to move, the Earth would respond immediately. Yet nothing else in nature behaved this way. Light takes time to travel. Radio signals take time. Even the fastest known influences respect a finite speed. Gravity alone stood apart, incompatible with the emerging structure of causality. The classical law offered no way out of this conflict. It contained no provision for delay, no mechanism for propagation. It simply worked as written. This revealed a critical limitation. The law was not wrong within its tested domain, but it was incomplete. It relied on assumptions about space and time that experiments were actively dismantling. Another limitation appeared in the precision of astronomical observation. As measurements improved, tiny discrepancies emerged that could not be ignored. The orbit of Mercury, the innermost planet, exhibited a slow shift in its closest approach to the Sun. Most of this motion could be explained by gravitational interactions with other planets. But a small remainder persisted. It was real, measurable, and resistant to correction. This discrepancy was not large. It did not cause Mercury to wander unpredictably. But physics does not dismiss small errors when they are systematic. A theory that explains almost everything but fails consistently in one place is signaling that something deeper is missing. Attempts were made to account for the anomaly by adding unseen matter or adjusting parameters, but these fixes lacked independent evidence. The problem was not Mercury itself. It was that gravity, as a force acting within fixed space and time, could no longer account for every observation without strain. The theory required patches rather than principles. Each patch weakened confidence that the force-based picture captured the true structure underlying gravitational phenomena. As physics moved forward, it became clear that gravity was being asked to coexist with ideas it could not naturally accommodate. Space and time were no longer passive arenas. They were dynamic, interwoven, and responsive to motion and energy. Treating gravity as something that merely acted within them began to feel conceptually backward. The force-based description had reached the edge of its usefulness. It remained an excellent approximation. It remained indispensable for calculation. But it could not survive unchanged in a universe where the geometry of space and time itself was no longer fixed. The question was no longer whether gravity worked. The question was whether it had been framed in the wrong language from the beginning. The cracks in the force-based picture were not isolated problems. They pointed toward a deeper inconsistency in how gravity had been framed from the start. Classical gravity treated space as a rigid backdrop and time as a universal clock, yet growing evidence showed that neither assumption held under closer scrutiny. Space could stretch and contract. Time could slow and speed up. Motion and measurement were inseparable. Gravity, defined as a force acting within this background, now appeared out of place. One of the most revealing difficulties involved energy and momentum. In other interactions, forces exchange energy through well-defined carriers. When two charged particles interact, energy is transferred through electromagnetic fields. These fields store energy, carry momentum, and propagate at a finite speed. Gravity, in its classical form, had no such structure. There was no gravitational field with local energy content that could be clearly defined in the same way. The bookkeeping of energy became ambiguous, especially when gravity interacted with motion at high speeds. This ambiguity was not merely technical. Conservation laws lie at the heart of physics. If a theory cannot cleanly account for how energy and momentum flow, it signals that the underlying description may be incomplete. Gravity worked numerically, but conceptually, it resisted being integrated into the same framework that unified other forces. Another issue emerged when considering reference frames. In classical mechanics, forces depend on the observer's frame of motion. In accelerating frames, fictitious forces appear. A person in a turning car feels pushed outward. An object on a rotating platform seems to drift sideways. These effects are not caused by physical interactions. They arise from the choice of reference frame. Gravity behaved strangely similar to these fictitious forces. In an accelerating elevator, objects fall toward the floor in exactly the same way they do in a gravitational field. From inside, there is no experiment that distinguishes acceleration from gravity. This was not a coincidence. It was a measured equivalence. Gravity could be locally transformed away by choosing a freely falling frame. No other force allowed this. This observation struck at the heart of the force-based interpretation. If gravity could be removed by changing perspective, then perhaps it was not a force in the same sense as others. Forces usually persist regardless of frame. Electric and magnetic effects do not disappear simply because one chooses to fall alongside a charged particle. Gravity did. The implication was subtle but radical. Gravity might not be something that acts on objects. It might instead reflect something about how motion itself is defined in the presence of mass and energy. The apparent force could be a consequence of using a frame that is not following the natural paths available to objects. Attempts to preserve the classical picture grew increasingly strained. Additional assumptions were introduced to reconcile gravity with finite signal speeds. Hypothetical mechanisms were proposed, but none were supported by independent evidence. Each adjustment addressed a symptom without resolving the cause. What had once been a strength now became a liability. The force-based description of gravity was too rigid. It required space and time to remain passive and absolute, even as experiments demonstrated that they were neither. Gravity was being squeezed into a conceptual structure that no longer matched the observed universe. By this point, the question was no longer whether gravity needed refinement. It was whether the entire notion of gravity as a force had been a convenient approximation rather than a fundamental truth. The evidence did not demand abandoning the successful calculations, but it did demand rethinking what those calculations actually described. Gravity still governed motion with remarkable precision. Apples fell, planets orbited. Yet beneath this stability, the conceptual ground had shifted. The force-based picture had reached its limit, not because it failed outright, but because it could no longer coexist with the deeper structure of space and time revealed by experiment. The remaining inconsistencies were subtle, but physics advances on subtleties. A theory can survive rough tests while quietly failing the most demanding ones. Gravity, treated as a force, now faced precisely this situation. It worked where space and time could be approximated as fixed. It struggled where those approximations broke down. One of the most revealing tensions appeared when gravity was compared to inertial motion. In the absence of forces, objects move in straight lines at constant speed. This principle had been tested endlessly and never violated. Yet gravity caused objects to accelerate even when no local interaction could be detected. The acceleration appeared built into the situation itself rather than imposed by an external agent. This blurred the distinction between natural motion and forced motion. In classical physics, straight-line motion was considered natural, while curved motion required explanation. Gravity inverted this logic. Objects influenced by gravity followed curved paths without experiencing resistance or stress. Free fall felt natural. Being held still felt artificial. The ground pushing upward produced strain. Gravity did not. This inversion hinted that gravity might be describing the structure of motion rather than an interaction layered on top of it. The force language remained useful, but it no longer felt fundamental. It described deviations from intuition rather than causes rooted in physical entities. The problem extended further when gravity was asked to coexist with the principle that the laws of physics should look the same in all locally inertial frames. In a small, freely falling laboratory, the effects of gravity vanish. Clocks tick normally. Objects drift as they would in empty space. No experiment performed within such a region can reveal the presence of a gravitational field. This was not an approximation. It was exact, as far as measurement could determine. Forces do not normally behave this way. One cannot eliminate an electric field by choosing a clever frame of motion. One cannot remove magnetism by falling alongside it. Gravity alone could be made to disappear locally. This was not a failure of measurement. It was a clue. By the early 20th century, gravity had become an outlier. It resisted unification with other forces. It conflicted with the emerging structure of spacetime. It behaved like inertia rather than interaction. Each of these facts pointed in the same direction. The force-based description was not wrong, but it was provisional. What physics required was not a correction to the law of gravity, but a reframing of what the law was actually describing. The empirical regularities were solid. The predictions were reliable. But the interpretation had reached its limit. Gravity had been treated as something that happens within space and time. The evidence increasingly suggested that gravity was inseparable from how space and time themselves behave. The failure was not in the data, but in the conceptual boundary that separated gravity from geometry. At this point, gravity ceased to be merely a force that required refinement. It became a signpost. It pointed toward a deeper structure in which motion, space, and time were no longer independent ingredients, but aspects of a single physical framework. The reframing of gravity did not begin with abstract mathematics or philosophical speculation. It began with an observation so simple that it had been overlooked for centuries. When gravity acts alone, without interference, all objects fall in exactly the same way. This statement is not poetic and not approximate. It is an experimental fact tested again and again with increasing precision. No matter what an object is made of, no matter how complex its internal structure, its motion in a gravitational field is identical to every other object when other effects are removed. This behavior is deeply counterintuitive when viewed through the lens of force. Forces usually depend on properties. Electrical forces depend on charge. Magnetic forces depend on orientation and motion. Friction depends on surfaces. Even resistance to acceleration depends on mass. Yet gravity ignores all of this detail. A massive block of metal and a fragile piece of glass fall together. A dense object and a hollow one trace the same path. Gravity does not select. It applies universally. This universality was recognized long before it was understood. Experiments comparing falling bodies date back centuries. As measurement improved, the equality became sharper rather than weaker. By the time laboratory instruments reached high precision, any difference in gravitational response between materials had become vanishingly small. Within experimental limits, inertial mass and gravitational mass were indistinguishable. Objects resisted acceleration in proportion to the same quantity that determined how strongly gravity acted on them. This equality is not assumed. It is measured. Torsion balance experiments, refined over generations, compared how different materials responded to Earth's gravity. The results showed no detectable difference. Later, satellite-based experiments extended this confirmation beyond Earth, testing free fall in orbit with extraordinary sensitivity. Again, no deviation appeared. Gravity treated all matter the same. The consequence of this fact was subtle but profound. If gravity were a conventional force, then its strength should depend on some intrinsic property beyond mere existence. Yet no such property could be found. The very quantity that measures resistance to acceleration also measured gravitational response. There was no way to separate the two experimentally. They were the same within every limit that could be tested. This led to an unexpected conclusion. The motion of an object in a gravitational field does not depend on the object. It depends on the environment. Gravity does not push objects differently based on what they are. It shapes the conditions under which motion occurs. Objects merely respond by following the same paths. This insight became clearer when considering accelerated motion. An observer inside a closed laboratory cannot distinguish between being at rest in a gravitational field and accelerating uniformly through empty space. A dropped object falls toward the floor in both cases. A clock behaves the same way. A beam of light curves identically. No internal experiment can tell the difference. This equivalence is exact in sufficiently small regions. What made this remarkable was not that gravity resembled acceleration, but that acceleration could reproduce gravity perfectly. This was not analogy, it was equivalence. Gravity could be transformed away locally by choosing a freely falling frame. In such a frame, the laws of physics reduce to those of special relativity. Gravity disappears, not globally, but locally, everywhere. This behavior had no parallel among other forces. One cannot eliminate an electric field by falling alongside it. One cannot make magnetism vanish by changing frames. Gravity alone could be removed by free fall. This was not a mathematical trick. It was an experimental fact. The equivalence principle did not explain gravity. It described how gravity behaves. It stated that locally, gravitational motion is indistinguishable from inertial motion. This single statement carried enormous weight. It implied that gravity was not acting on objects in the usual sense. It was redefining what straight motion meant in the first place. Gravity had ceased to look like a force imposed on matter. It now looked like a property of motion itself. Objects in free fall were not being pulled. They were moving naturally. The sensation of weight arose only when that motion was prevented. The ground pushing upward created force. Gravity did not. This principle was not philosophical. It was enforced by experiment. And once accepted, it left no room for gravity to remain what it had been. The equivalence between gravity and inertia demanded a new description, one in which the distinction between force and geometry could no longer be taken for granted. The implications of this equivalence reached far beyond falling objects. If gravity and acceleration were locally indistinguishable, then gravity could not be understood as something acting within space and time. It had to be connected to the structure of space and time themselves. This was not a philosophical leap. It was a logical consequence forced by measurement. Consider light. Light does not have mass in the usual sense, yet it responds to gravity. A beam of light passing near a massive object bends. This bending can be predicted precisely. But from the perspective of an accelerating frame, the same bending appears even in the absence of any mass at all. Inside an accelerating laboratory, a light beam curves downward relative to the observer. The mathematics and the observation match exactly. Gravity and acceleration produce the same effect on light. This mattered because light defines the structure of space-time itself. Distances and times are measured using light signals. If gravity affects light in the same way acceleration does, then gravity must influence the very framework used to define measurement. It is not merely something added on top of space and time. It participates in their definition. The equivalence principle therefore carried a quiet but radical message. In a small enough region of space-time, gravity can always be eliminated. There exists a frame in which objects move freely, clocks tick normally, and light travels in straight lines. These frames are not special locations. They exist everywhere. Any observer in free fall occupies one. This means that gravity has no local fingerprint. It cannot be detected by any experiment confined to a sufficiently small, freely falling region. Forces usually reveal themselves locally. An electric field can be detected at a point. A magnetic field can be measured at a point. Gravity cannot. It only reveals itself through differences between neighboring paths. Two objects dropped side by side may drift closer or farther apart as they fall. This relative motion, not the motion itself, contains information about gravity. Gravity shows up not as acceleration, but as variation in acceleration. This distinction is crucial. It shifts attention away from forces acting on individual objects and toward relationships between nearby trajectories. Gravity does not dictate how one object moves in isolation. It dictates how collections of nearby objects move relative to one another. The effect is geometric rather than dynamical in the usual sense. At this stage, gravity had acquired a new identity. It was no longer something that could be fully described by assigning a force to each object. It was something that shaped the arena in which motion occurred. Objects in free fall followed paths that were locally straight, even if those paths curved when viewed over larger regions. The curvature did not signal force, it signaled structure. This idea resolved several earlier puzzles at once. The universality of freefall became natural. If gravity is geometry, then all objects follow the same paths, regardless of their internal composition. The inability to shield gravity ceased to be mysterious. One cannot shield geometry. The disappearance of gravity in freely falling frames was no longer paradoxical. One cannot feel geometry locally any more than one can feel the curvature of Earth while standing on a flat patch of ground. None of this required abandoning experiment. On the contrary, it was demanded by experiment. The equivalence principle was not a speculative proposal. It was a summary of what nature consistently revealed. Every attempt to find a violation failed. The principle survived tests with ever-increasing precision. Gravity had now been stripped of the characteristics that define ordinary forces. It did not act selectively. It did not announce itself locally. It could be transformed away by free fall. It affected light and matter in the same way. These facts did not yet provide a full theory, but they narrowed the possibilities dramatically. The remaining step was unavoidable. If gravity could be removed locally, yet still produced observable effects over extended regions, then those effects had to arise from something that could not be transformed away everywhere at once. The only candidate left was the structure of spacetime itself. Gravity was no longer acting within spacetime. It was shaping it. In this picture, freely falling objects are not being pulled. They are following the straightest possible paths available to them. These paths only appear curved when compared across larger regions. Locally, motion is inertial. Globally, paths diverge or converge because the geometry they pass through is not flat. The apparent force of gravity emerges when objects are prevented from following these natural paths. This resolved the puzzle of weight. Standing on the ground feels like a force because the ground is pushing upward, forcing the body away from its natural trajectory. The strain in muscles, the pressure on feet, the resistance felt by structures all arise from this interruption. Gravity itself produces no strain. The sensation of weight is not caused by falling, but by not falling. The same reasoning explained why gravity could influence light. Light follows the straightest possible paths permitted by spacetime geometry. When spacetime is curved, those paths bend. Light does not slow down or feel a force. It simply follows the geometry available to it. The bending of starlight near massive objects was no longer mysterious. It was a geometric effect. Crucially, this interpretation did not discard the classical predictions. It explained why they worked. In regions where spacetime curvature is weak, the geometric description reduces to the familiar force-based law. The old equations emerge as approximations, not mistakes. They remain valid where their assumptions hold. The equivalence principle thus became more than a statement about falling objects. It became a guidepost. It told physicists what gravity could not be. Gravity could not be a force like others. It could not act locally in the usual way. It could not depend on internal composition. Whatever gravity was, it had to be woven into the structure of spacetime itself. This conclusion was not metaphysical. It was enforced by experiment. Every precise test of free fall, every comparison of clocks, every observation of motion under gravity reinforced the same message. The language of force had reached its limit. A new language was required, one capable of describing how space and time respond to mass and energy. Gravity had begun as a familiar pattern. It became a precise law. It resisted explanation as a force. Through the equivalence principle, it finally revealed its true character. Not as something that pushes or pulls, but as something that shapes the paths along which all motion unfolds. Once gravity was understood as inseparable from motion itself, the focus of explanation shifted naturally toward the stage on which all motion occurs. Space and time, long treated as passive backgrounds, could no longer remain untouched. If gravity shapes how objects move without acting as a force, then something deeper must be changing. that something is space-time. For centuries, space and time had been assumed rather than examined. Space was an empty container in which objects existed and moved. Time flowed uniformly, ticking forward at the same rate everywhere, independent of motion or location. These ideas felt obvious because they matched everyday experience. They worked well enough that no one questioned them deeply until experiments forced the issue. The behavior of light was the first clear signal that these assumptions were wrong. Light does not behave like ordinary objects. Its speed is always the same, regardless of the motion of the source or the observer. This fact was not guessed. It was measured, repeatedly. To preserve this consistency, space and time could not remain independent. They had to adjust together. Lengths contract when objects move rapidly. Clocks tick at different rates depending on motion. Events that appear simultaneous to one observer are not simultaneous to another. These effects are not illusions. They are real, measurable consequences of how space-time behaves. Space and time are not separate ingredients. They form a single structure that responds to motion. Once this was accepted, the idea that space-time might also respond to mass and energy became unavoidable. If motion can reshape measurements of distance and duration, then mass and energy might do the same. Gravity was no longer something acting inside space-time. It was something acting on space-time. This shift was subtle but profound. Space-time ceased to be an abstract mathematical convenience. It became a physical entity, something with measurable properties. Its geometry could change. Its structure could curve. And those changes could influence the motion of matter and light. Crucially, this was not a philosophical declaration. It was a demand imposed by consistency. The equivalence principle had shown that gravity disappears locally in free fall. The behavior of light had shown that space-time defines measurement itself. The only framework that could accommodate both facts was one in which space-time geometry was dynamic. In this view, mass and energy do not pull on objects directly. They alter the geometric relationships between events. They change which paths are straight and which are curved. Objects in free fall follow the straightest paths available, paths defined by the geometry of space-time rather than by external forces. This interpretation resolved earlier puzzles without adding new assumptions. The universality of free fall followed naturally. All objects respond the same way because geometry does not care about composition. The inability to shield gravity became obvious. One cannot block geometry any more than one can block distance or time. The disappearance of gravity in freely falling frames became expected. Locally, space-time always looks flat. Space-time, once thought of as nothing more than an empty arena, had become an active participant. It could stretch, contract, and curve. Its geometry carried physical meaning. And gravity, rather than being an interaction layered on top of reality, emerged as a manifestation of this geometry. The realization that space-time could curve transformed gravity from a mysterious influence into a structural property of the universe. Curvature was no longer a metaphor or a mathematical trick. It became something that could be inferred from observation. If space-time geometry determines motion, then changes in motion reveal changes in geometry. Geometry became measurable through its consequences. This required a careful distinction. Curvature does not mean that space bends into some higher dimensional arena. That image is often used for visualization, but it is not what is physically meant. Curvature refers to relationships between distances and times measured within space-time itself. It describes how the rules of geometry differ from those of flat space. Parallel paths may converge or diverge. Straight lines may not remain straight when extended. These effects can be detected without stepping outside space-time. One of the most important tools for recognizing curvature is the behavior of nearby trajectories. In flat space-time, objects released side by side remain side by side. Their separation stays constant. In curved space-time, this is no longer true. Two objects in free fall may slowly drift together or apart, even though neither experiences any force. This relative motion is not caused by interaction between the objects. It is caused by the geometry they move through. This phenomenon is measurable. It produces tidal effects. Oceans rise and fall, not because gravity pulls harder on water than on land, but because different parts of Earth follow slightly different paths through curved space-time. The same effect stretches objects near massive bodies. These are not secondary details. They are direct signatures of curvature. Time itself is also affected. Clocks placed at different heights in a gravitational field tick at different rates. This is not because gravity slows clocks mechanically. It is because space-time geometry assigns different time intervals to different paths. A clock measures the length of its path through space-time. When geometry changes, those lengths change as well. These effects are not small curiosities. They are measured routinely. Satellite navigation systems must account for them to function correctly. Atomic clocks separated by changes in altitude show differences exactly matching the predictions of curved space-time. The geometry is not inferred indirectly. It is confirmed operationally through measurement. This marked a fundamental shift in how physical reality was described. Geometry was no longer separate from physics. It was physics. Distances and durations were no longer fixed backdrops. They were outcomes of space-time structure. Gravity, once treated as a force acting across space, was now understood as the manifestation of that structure. Importantly, this did not mean that coordinates themselves carried physical meaning. Different observers may describe space-time using different coordinate systems. The curvature does not depend on these choices. It is invariant. It can be detected by any observer through local experiments involving relative motion and clock comparison. Space-time had become something that could be probed, measured, and tested. It responded to mass and energy. It influenced motion, and it did so in a way that preserved the equivalence principle and the observed universality of gravity. The framework was no longer one of forces acting at a distance, but of geometry guiding motion. The final step was to understand how this geometric picture could remain consistent with everything that had already been tested. A new description of gravity would be meaningless if it failed, where the old one succeeded. Any deeper framework had to reproduce familiar results in ordinary conditions, while extending naturally into regimes where classical ideas broke down. This requirement imposed strict discipline. In regions where space-time curvature is weak, where gravitational fields are gentle and motions are slow, the geometry must look nearly flat. In such regions, the straightest paths through space-time differ only slightly from the straight lines of classical physics. When described in everyday language, these slight deviations appear exactly as a force pulling objects downward. The familiar equations emerge automatically, not as fundamental laws, but as approximations. This explained why the classical description had worked so well for so long. It was never wrong within its domain. It was incomplete. It described the behavior of motion in a space-time whose curvature was too subtle to notice directly. As measurements improved and new regimes were explored, the limitations of that approximation became visible. The geometric picture also clarified why gravity interacts with energy in all its forms. Light, pressure, and even internal motion contribute to space-time curvature. Gravity does not single out mass alone. Anything that carries energy or momentum influences geometry. This was not an added assumption. It followed from the requirement that space-time respond consistently to everything that defines physical processes. Crucially, this framework preserved causality. Changes in space-time geometry propagate at finite speed. Gravitational influence does not act instantaneously. Disturbances travel through space-time just as other physical effects do. The conflict with relativity disappeared, not by modifying gravity arbitrarily, but by embedding it within the same structure that governs all motion and measurement. Space-time, once regarded as an empty container, now carried dynamics. It could evolve, it could ripple, it could respond, and those responses had observable consequences. Motion was no longer imposed upon geometry. Motion emerged from geometry. This did not settle every question. It did not explain why spacetime has the properties it does. It did not reveal whether geometry itself is fundamental or emergent. Those questions lay beyond experimental reach. What mattered was that the new description matched observation precisely and coherently. Gravity had completed a transformation, from a familiar downward pull to a universal rule, from a force acting across distance to a manifestation of curved space-time. Each step was forced by evidence, not by interpretation. Each revision preserved what was measured and discarded only what could no longer be sustained. Spacetime was no longer passive. It was a physical entity with structure, behavior, and measurable effects. And gravity, once an observed phenomenon without explanation, had become inseparable from that structure itself. Once spacetime is understood as a physical entity with structure, the meaning of motion itself begins to change. In everyday language, motion usually implies cause. Something moves because something pushes or pulls it. Acceleration demands a force. This intuition works well in daily life, but gravity has already shown that it does not obey this pattern. In the geometric picture, motion under gravity requires no force at all. To see why, it helps to reconsider what is meant by a straight path. In flat space, a straight line is obvious. It is the shortest distance between 2 points. Objects moving without interference follow such lines naturally. In curved space, the idea of straightness still exists, but it takes a different form. The straightest possible path is no longer what intuition suggests. It is defined by the geometry itself. These straightest paths are called geodesics. They are not imposed by forces. They arise from the structure of space-time. An object moving freely simply follows one. No energy is expended to stay on this path. No signal instructs the object where to go. Motion unfolds as a consequence of geometry alone. This is why free fall feels effortless. An object dropped from rest is not being dragged downward. It is moving along a geodesic through space-time shaped by the Earth. Locally, the motion is inertial. The object experiences no resistance, no strain, no force. The acceleration seen by an observer standing on the ground is not caused by gravity acting on the object. It is caused by the observer being prevented from following the same path. From this perspective, the sensation of gravity arises only when motion is constrained. The ground pushes upward on feet. A chair presses against the body. These contact forces create the feeling of weight. Gravity itself does not. The absence of gravity would not feel like floating. It would feel like being supported everywhere at once, which never happens. What we call weightlessness is simply the absence of constraint. This reinterpretation resolves a long-standing confusion. In orbit, astronauts are not beyond gravity. They are deep within it. The Earth shapes space-time strongly in their region. Yet they float because they are following geodesics. Their spacecraft and their bodies are falling together, tracing the same natural paths. Nothing pulls them toward the floor because there is no floor pushing back. Curved motion therefore no longer implies force. An object can follow a curved path while experiencing no force at all. The curvature belongs to space-time, not to the object's trajectory in isolation. The object merely responds to the geometry it inhabits. This also explains why gravity can influence light. Light follows geodesics as well. Its paths are determined entirely by space-time geometry. When geometry curves, light bends. It does not slow down. It does not feel a pull. It follows the straightest paths available, which appear curved when compared across regions of differing geometry. What appears from afar as attraction is, from within the system, simply motion unfolding naturally. The force language remains useful for approximation and calculation, but it is no longer fundamental. The deeper description requires no force term at all. It requires only geometry and the principle that free motion follows geodesics. The consequences of this shift are subtle but far-reaching. Once motion is understood as geodesic motion, many familiar ideas must be carefully re-examined. Acceleration, which once signaled the presence of a force, becomes observer-dependent. An object following a geodesic is not accelerating in any absolute sense. It accelerates only relative to observers who are themselves constrained. This distinction explains why observers at rest on Earth feel weight, while objects in free fall do not. The observer standing on the ground is not following a geodesic. The earth beneath their feet prevents that natural motion. The ground exerts an upward force, constantly pushing the observer away from the geodesic they would otherwise follow. The sensation of gravity arises from this upward force, not from gravity acting downward. From this viewpoint, gravity does not cause acceleration. Resistance to gravity does. Floors, chairs, and surfaces impose acceleration by preventing free fall. Gravity sets the geometry. Matter responds by moving freely within it whenever possible. When that freedom is removed, force appears. This reinterpretation also clarifies why gravity cannot be eliminated globally. While a freely falling observer can always remove gravity locally, no single frame can remove it everywhere. Over extended regions, geodesics that begin parallel do not remain parallel. They converge and diverge. This relative behavior cannot be transformed away. It is an intrinsic property of curvature. These relative effects are what we call tidal phenomena. Near Earth, tides stretch oceans and deform solid ground. Near compact objects, they become extreme, pulling matter apart. Tidal effects are not additional forces layered on top of gravity. They are direct manifestations of space-time curvature. They arise because different parts of an object attempt to follow different geodesics. This explains why gravity can be detected only through differences. A single freely falling object reveals nothing. Two nearby objects reveal geometry. Their separation changes in ways that depend only on curvature, not on their composition. Gravity leaves no local signature. It reveals itself through relationships. This framework also resolves an apparent contradiction. In the classical picture, gravity pulls objects inward, yet no energy seems to be transferred locally. In the geometric picture, there is no energy transfer associated with free fall. Energy is conserved because nothing is acting on the object. The motion is inertial. Only when constraints are applied does energy flow through contact forces. The absence of a force term in the equations of motion is not a mathematical curiosity. It reflects a deep physical statement. Gravity is not something added to motion. It defines what unforced motion means. Objects in free fall are doing exactly what physics requires them to do in the geometry they inhabit. This perspective removes the need to ask how gravity pushes or pulls. It replaces that question with a different one. How does mass and energy shape space-time geometry? Once that geometry is known, motion follows automatically. The idea of force has not vanished. It remains essential for describing interactions that deviate from geodesic motion. Engines fire, muscles contract, electromagnetic forces act. But gravity no longer belongs in this category. It stands apart, not because it is mysterious, but because it is geometric. The geometric description also explains why gravity is so difficult to isolate or manipulate. Forces can be turned on or off. They can be screened, redirected, or cancelled. Geometry cannot. One cannot shield an object from the structure of space-time any more than one can shield it from distance or duration. Objects exist within geometry by necessity, not by interaction. This is why gravity has no negative counterpart. There is no opposite charge that repels gravitationally. Geometry does not come in opposing types. Curvature can vary in strength and sign, but it does not cancel in the way forces do. Mass and energy contribute to space-time structure in a cumulative way. Their effects add. They do not neutralize one another. The language of curvature also clarifies why gravitational influence weakens with distance without invoking a pulling mechanism. Far from a massive object, space-time geometry becomes nearly flat. Geodesics that begin parallel remain nearly parallel. The deviation from straightness becomes small. What appears as a weakening force is simply a gradual return toward flat geometry. Importantly, none of this requires imagining spacetime as a substance or medium in a mechanical sense. Spacetime is not something objects move through like water or air. It is the set of relationships that define where and when events occur. Curvature refers to how those relationships differ from flat expectations. It is measured through motion, not felt directly. This restraint matters. The geometric description is powerful because it avoids unnecessary imagery. It does not claim what spacetime is made of. It describes how it behaves. Physics remains anchored in what can be tested. Curvature is inferred from the paths of objects and the ticking of clocks. Nothing more is required. In this framework, gravity loses its role as a fundamental interaction and gains a new role as a structural feature. It governs motion not by acting on matter, but by defining the conditions under which matter moves freely. The equations of motion contain no gravitational force because none is needed. Geometry does all the work. This does not mean gravity is an illusion in the sense of being unreal. The effects are measurable and undeniable. Orbits exist. Tides occur. Clocks disagree. What changes is the interpretation. The apparent force is a consequence of describing motion from a constrained perspective. The underlying process is geometric. By this point, the question of gravity had been reframed completely. The issue was no longer how gravity reaches across space or why it pulls objects together. The central question had become how spacetime acquires its shape and how that shape evolves in response to mass and energy. Motion without force was no longer a paradox. It was the natural outcome of curved spacetime. Objects fall not because they are compelled, but because there is nowhere else for them to go. They follow the straightest possible paths in a geometry that is not flat. The geometric description of gravity would mean little if it remained a purely conceptual construction. Physics does not accept frameworks because they are elegant or internally consistent. It accepts them because they survive confrontation with experiment. The idea that space-time curvature replaces gravitational force faced this same requirement. It had to produce testable consequences that could be measured in the real world. One of the earliest and most direct predictions concerned time itself. If space-time geometry changes in the presence of mass and energy, then time should not flow uniformly everywhere. Clocks following different paths through spacetime should tick at different rates. This effect is not a metaphor. A clock measures the length of its path through spacetime. When geometry changes, those lengths change as well. Near a massive object, spacetime curvature alters the structure of time. A clock closer to the mass ticks more slowly than one farther away. This difference is not caused by mechanical interference or environmental disturbance. It arises even when the clocks are isolated from all non-gravitational influences. The effect depends only on position within the gravitational field. This prediction was tested directly using atomic clocks. Identical clocks placed at different heights were allowed to run for extended periods and then compared. The results matched the geometric prediction precisely. The clock closer to Earth lagged behind the one farther away by exactly the amount expected from space-time curvature. The difference was small, but it was real and repeatable. The same effect operates continuously in orbit. Satellites carry clocks that tick at rates different from clocks on the ground. Part of this difference arises from their motion. Part arises from their position in Earth's gravitational field. Both effects are predicted by the geometric description of space-time. Both must be accounted for simultaneously. This is not an academic detail. Satellite navigation systems rely on accurate timing to determine position. If gravitational time dilation were ignored, errors would accumulate rapidly. Positions would drift by kilometers each day. The fact that these systems work is a daily experimental confirmation that space-time curvature affects time exactly as predicted. Light provided another critical test. If gravity is geometry, then light should follow curved paths in the presence of mass. This bending is not caused by a force acting on light. It occurs because light follows geodesics defined by space-time structure. The amount of bending can be calculated precisely. This effect was first confirmed by observing starlight passing near the Sun during a solar eclipse. The apparent positions of stars shifted by the exact amount predicted. The measurement was difficult and required careful control of uncertainty, but the result was clear. Light does not travel in straight lines when space-time is curved. Further tests refined this result. Light passing near massive bodies experiences measurable delays. Signals sent near the Sun take slightly longer to travel than they would through flat space-time. This delay is not due to interference or scattering. It arises because the geometry lengthens the path through space-time. These delays have been measured using radio signals sent to spacecraft and reflected back to Earth. The timing matches the geometric prediction with extraordinary accuracy. Once again, space-time curvature reveals itself not through force, but through altered relationships between distance and time. The geometric description also predicts that changes in mass distribution should produce ripples in space-time itself. These disturbances propagate outward at finite speed. They are not forces traveling through space. They are changes in geometry moving through space-time. These ripples, known as gravitational waves, were detected directly by measuring tiny changes in distance between widely separated objects. The distortions were minuscule, far smaller than atomic dimensions, yet they matched the predicted patterns exactly. The signals carried information about violent cosmic events where space-time curvature changed rapidly. Each of these observations points to the same conclusion. Space-time curvature is not an abstract idea. It produces real, measurable effects. Time dilation, light deflection, signal delay, and gravitational waves are not separate phenomena. They are different expressions of the same underlying geometry. Gravity, described as curved space-time, is not a philosophical reinterpretation layered onto existing facts. It is a framework that makes precise predictions and survives experimental scrutiny. The force-based picture cannot account for these effects without additional assumptions. The geometric picture predicts them naturally. The confirmation of curved space-time did not arrive all at once. It accumulated gradually through experiments that tested different aspects of the same underlying idea. Each test examined a different consequence of geometry, and each one converged on the same result. Space and time respond to mass and energy in precisely the way the geometric framework predicts. One of the most striking confirmations comes from clocks that never touch the ground. Atomic clocks carried aboard aircraft and satellites tick at rates that differ measurably from clocks left on Earth. These differences are not random. They follow a precise pattern. Clocks higher above the Earth tick faster than clocks closer to the surface. The effect increases smoothly with altitude. No adjustment based on force alone can account for this behavior. It follows directly from space-time geometry. The comparison is not subtle in its implications. Two clocks built to be identical will disagree simply because they follow different paths through space-time. Time itself is stretched and compressed by gravity. This is not a feature of clocks. It is a feature of reality. The clocks merely reveal it. Light behaves in the same way. Signals traveling near massive bodies experience both bending and delay. The bending changes where objects appear in the sky. The delay changes how long signals take to return. These effects have been measured repeatedly using spacecraft ranging experiments. Radar pulses sent toward planets and reflected back take longer to return when their paths pass close to the Sun. The extra time is exactly what curved spacetime predicts. What matters here is not just that the predictions are correct, but that they require no additional mechanisms. There is no need to imagine gravity pulling on light or slowing clocks mechanically. The geometry alone accounts for the observations. Once spacetime structure is specified, the behavior of clocks and signals follows automatically. The same principle applies on much larger scales. Massive objects, such as galaxies, bend light from more distant sources, producing multiple images and distorted arcs. These effects, known as gravitational lensing, allow astronomers to map spacetime curvature directly. The lensing patterns depend only on geometry. They reveal how mass and energy are distributed, even when that mass cannot be seen directly. These observations provide independent confirmation that geometry governs motion. The bending of light around galaxies does not depend on the composition of the light or the properties of the source. It depends only on the structure of spacetime along the path. Once again, universality emerges naturally. Even the passage of time on Earth itself carries the imprint of curvature. Measurements show that time flows at slightly different rates between sea level and mountain tops. The difference is tiny, but it is real and consistent. Time is not a universal background ticking identically everywhere. It is shaped by gravity in a measurable way. Taken together, these results leave little room for alternative interpretations. Gravity produces effects that cannot be explained as forces acting within a fixed space-time. The effects are geometric at their core. They alter how distance and duration are defined. They influence motion without acting locally on objects. By the time these experiments were complete, gravity had crossed a threshold. It was no longer a hypothesis about geometry. It was an empirically supported description of reality. Curved spacetime was not an abstract mathematical construct. It was a physical framework confirmed by clocks, light, and motion across scales, ranging from laboratories to galaxies. The final confirmation came from phenomena that could not be produced in any static picture of gravity at all. If spacetime geometry is truly physical, then it should be capable of change. And if it can change, those changes should propagate outward, carrying information about their source. This was one of the most demanding predictions of the geometric description, and for a long time it remained beyond experimental reach. When massive objects accelerate, especially in violent cosmic events, the geometry around them cannot adjust instantaneously everywhere. The change must spread. These propagating changes are not forces traveling through space. They are distortions of spacetime itself, moving outward at finite speed. Their existence follows directly from the requirement that gravity respect the same causal structure as all other physical processes. The detection of these distortions required extraordinary precision. Instruments were built to measure changes in distance far smaller than the size of an atomic nucleus, over separations of kilometers. When the signals finally appeared, they carried a distinctive pattern. The stretching and squeezing of spacetime occurred exactly as the geometric framework predicted. The timing, the shape, and the strength of the signals matched calculations based solely on spacetime curvature. These observations were not isolated events. They were repeated. Each detection carried information about distant systems where spacetime curvature changed rapidly. Colliding compact objects produced ripples that traveled across the universe and reached Earth after millions or billions of years. The signals arrived with no loss of structure. Geometry had carried them faithfully across cosmic distances. What made these observations decisive was not just that something was detected, but that what was detected could only be interpreted as changes in spacetime itself. There was no alternative force-based explanation that could reproduce the observed patterns without introducing unsupported assumptions. The geometry was not inferred indirectly. It was measured through its direct dynamical behavior. By this point, gravity as curved spacetime had been tested in every regime accessible to experiment. Time dilation near Earth, light deflection near the Sun, signal delays across the solar system, lensing across galaxies, dynamic spacetime ripples from distant cosmic events. Each phenomenon confirmed a different aspect of the same framework. The consistency was remarkable. A single geometric description accounted for all of it. No new parameters were required. No special cases had to be added. The predictions emerged from the structure of spacetime itself, once mass and energy were specified. Gravity, once understood as a force pulling objects together, had been replaced by a deeper description grounded entirely in measurable effects. Spacetime curvature was not an interpretive overlay. It was the simplest framework that explained all confirmed observations without contradiction. This did not mean that gravity had been reduced to geometry in a philosophical sense. It meant something more precise. The The behavior we call gravity is fully captured by the geometry of spacetime within the limits of current experiments. Every test conducted so far agrees with this description. The question of whether geometry is fundamental or emergent remained open. Experiments could not answer that, but they answered something equally important. They showed that treating gravity as curved spacetime is not an illusion created by mathematics. It is a description forced upon us by nature itself. When gravity is understood as spacetime geometry, the most extreme gravitational environments must also be understood geometrically. Black holes are not objects that pull harder than anything else. They are solutions to the equations that describe how spacetime can be shaped by mass and energy. They represent regions where curvature becomes so intense that familiar notions of space and time cease to behave in familiar ways. The idea of a black hole did not emerge from speculation or imagination. It emerged from mathematics constrained by physical principles. When the geometric equations of gravity are applied to a sufficiently compact mass, they allow a solution in which spacetime becomes so strongly curved that all future directed paths point inward. This inward direction is not spatial in the ordinary sense. It is temporal. Once crossed, it cannot be avoided, not by matter, not by light, not by any physical process consistent with known laws. At the boundary of such a region lies what is called the event horizon. This boundary is not a physical surface. Nothing special happens to an object crossing it locally. There is no sudden force, no barrier, no flash of energy. A freely falling observer passes through without noticing anything unusual at that moment. The geometry remains smooth. The laws of physics continue to operate normally in their local form. The event horizon is defined not by what happens there, but by what cannot happen beyond it. Signals sent outward from inside the horizon never reach distant observers. Paths that once allowed escape no longer exist. This is not because of a force pulling inward, but because space-time geometry has reshaped the structure of possible futures. Outside the horizon, paths can lead away. Inside, all future paths lead deeper inward. This distinction is purely geometric. It depends on the structure of space-time, not on local interactions. An observer falling into a black hole feels weightless, just as they would in orbit around Earth. The difference is not felt locally, it is encoded globally in the geometry. This feature highlights a crucial point. Gravity does not become stronger in the sense of exerting greater force at the horizon. In fact, at the horizon of a sufficiently large black hole, tidal effects can be extremely small. Nothing dramatic announces the crossing. The danger lies not in force, but in inevitability. The geometry has removed all outward directed futures. Black holes therefore provide a clear demonstration that gravity is not fundamentally about pulling. If gravity were a force, one would expect the horizon to be marked by infinite stress or infinite acceleration. It is not. The defining property of a black hole is not local violence, but global structure. These solutions also show that spacetime can contain boundaries defined entirely by geometry. The horizon is not a place where matter accumulates. It is a boundary in causal structure. It separates regions that can communicate with the rest of the universe from those that cannot. What makes black holes scientifically compelling is not just their mathematical elegance, but their observational support. Stars orbiting invisible massive objects follow paths that can only be explained by extreme space-time curvature. Signals from accreting matter behave exactly as predicted by geometric models. The geometry is not hypothetical. It is inferred directly from motion and light. Black holes thus represent gravity in its purest geometric form. No force acts at the horizon. No mechanism pushes inward. Spacetime itself defines what motion is allowed. Matter and light simply follow the paths available to them. The observational evidence for black holes strengthens this geometric picture rather than challenging it. Stars near the centers of galaxies, move along precise, predictable paths around regions where no visible object exists. Their speeds increase dramatically as they approach these unseen centers, yet their motion remains smooth and orderly. There is no sign of chaotic pulling or sudden force. The paths follow exactly what curved spacetime predicts for motion around an extremely compact mass. In these systems, gravity does not behave differently near the horizon than it does farther away in any local sense. What changes is the global structure of spacetime. Orbits that once could exist no longer do. Stable paths disappear. Matter spirals inward, not because it is dragged, but because the geometry no longer supports outward trajectories. This becomes especially clear when considering rotation. When a massive object spins, spacetime does not remain static. It is dragged along with the rotation. This effect does not resemble friction or torque in the ordinary sense. It is a geometric phenomenon. Paths through spacetime are twisted. Objects nearby are compelled to rotate, not by force, but because remaining stationary is no longer a valid path. This behavior has been measured. Matter orbiting rotating black holes exhibits motion that cannot be explained by Newtonian gravity or by any force acting through space alone. The geometry itself carries angular structure. Space-time acquires a directional character that influences all nearby motion. Once again, the absence of force is central. Objects do not feel a rotational pull. They follow the only available geodesics. The distinction between being carried along and choosing to remain still vanishes. Geometry dictates what stillness means. Light reveals this most clearly. Near black holes, light paths curve, loop, and in some cases orbit temporarily before escaping or falling inward. These trajectories are calculated entirely from space-time geometry. No interaction with matter is required. The light responds only to structure. Images of glowing matter near black holes confirm these predictions. Rings, shadows, and distortions appear exactly where geometry demands they should. The darkness at the center of these images is not caused by absorption. It is caused by the absence of paths that allow light to escape. The geometry removes those paths. Black holes therefore do not represent gravity becoming stronger as a force. They represent gravity becoming dominant as geometry. The familiar idea of attraction loses meaning. What remains is structure. Space-time itself has been shaped into a form that admits only one future direction for anything that enters. This perspective also clarifies why black holes are stable solutions rather than transient catastrophes. Once formed, their geometry persists. They do not require continuous input of force. They exist because the equations describing spacetime permit such configurations. Matter may fall in, radiation may escape, but the underlying structure remains, unless altered by new mass or energy. Black holes thus serve as laboratories for gravity, stripped of every unnecessary concept. No force terms, no instantaneous action, no hidden mechanism, only geometry and motion. They demonstrate that gravity reaches its most extreme expression, not through violence, but through inevitability built into the structure of space-time itself. The final and most striking confirmation of black holes as geometric entities comes from how space-time itself responds when these objects interact. When two compact, massive bodies orbit each other and merge, the geometry around them does not remain static. It evolves dynamically, reshaping itself in response to the changing distribution of mass and energy. The resulting motion is not chaotic. It follows precise patterns dictated entirely by space-time structure. As these objects spiral closer together, their surrounding geometry becomes increasingly distorted. Paths that once existed are stretched and twisted. Distances oscillate. Time itself is affected. These changes propagate outward through spacetime, carrying information about the system that produced them. What travels outward is not matter and not force. It is geometry in motion. The signals detected from such events match this description exactly. They encode the masses, spins, and orbital dynamics of the merging bodies. Every detail of the signal corresponds to predictions derived from geometric equations. There is no freedom to reinterpret these observations as forces acting at a distance. The information is carried by spacetime itself. This is a crucial point. Black holes do not merely confirm that gravity can be described geometrically. They show that geometry can behave dynamically, carrying energy and information across the universe. Spacetime is not frozen. It is responsive. It evolves according to precise rules that can be tested experimentally. Equally important is what does not happen at black holes. There is no detectable surface where gravity becomes infinite in a physical sense. Outside the deepest interior regions, spacetime remains well behaved. Observers falling inward experience nothing locally catastrophic at the horizon. The breakdown appears only when extending the description beyond where current theories remain valid. This distinction matters because it reinforces the central theme. Gravity does not announce itself through local force. It reveals itself through global structure. Black holes are defined not by what they do to objects at a point, but by how they rearrange the space of possible futures. In this way, black holes complete the transition that began with falling objects and planetary motion. What started as a familiar downward tendency became a force law. That force law gave way to equivalence. Equivalence demanded geometry. Geometry, when pushed to its limits, produced black holes. These objects are not exceptions to the geometric description. They are its most natural outcome. They show that spacetime can adopt configurations in which escape is not prohibited by strength, but by structure. Nothing is pulled in. Everything simply follows the only paths that remain. Black holes therefore stand as the clearest demonstration that gravity is not fundamentally a force. Where gravity is strongest, force language becomes least appropriate. Geometry alone remains meaningful. When gravity is understood as geometry, its influence cannot be confined to stars, planets, or black holes alone. Geometry does not stop at the edge of a system. It extends everywhere. If spacetime can curve locally around mass and energy, then it must also possess a large-scale structure. The universe itself must have a geometry, and gravity must play a central role in shaping it. For much of human history, the universe was assumed to be static and unchanging on the largest scales. Stars appeared fixed. The sky seemed eternal. Space was treated as an infinite, empty backdrop in which matter was scattered. This assumption did not arise from evidence. It arose from familiarity. Nothing in daily experience suggested otherwise. As observations improved, this picture began to dissolve. Distant galaxies were found to be moving relative to one another. The farther away a galaxy was, the faster it appeared to recede. This motion was not random. It followed a precise pattern. Space itself was expanding. This expansion is not like an explosion from a central point. There is no center. Every region sees other distant regions moving away. The geometry of spacetime is changing everywhere at once. Distances between widely separated galaxies increase not because galaxies are moving through space, but because the space between them is stretching. This behavior cannot be explained by forces acting between galaxies alone. Galaxies are bound internally by gravity. Their stars orbit normally. Their structures remain intact. The expansion appears only on large scales, where local gravitational binding gives way to the overall geometry of the universe. In the geometric description, this behavior is natural. Spacetime has its own dynamics. Its large-scale curvature evolves according to the distribution of mass and energy throughout the universe. Expansion is not something imposed from outside. It is a solution allowed by the same equations that describe gravity near Earth and near black holes. Gravity plays a dual role on cosmic scales. Locally, it pulls matter together, allowing stars and galaxies to form. Globally, it participates in shaping the overall geometry that governs expansion. These roles are not contradictory. They arise from the same underlying structure. The evidence for this geometric behavior comes from multiple, independent observations. The light from distant galaxies carries information about how spacetime has changed over time. The distribution of galaxies reveals patterns imprinted by early gravitational processes. The faint background radiation filling the universe records conditions when spacetime was young and nearly uniform. Each of these observations points to the same conclusion. Gravity is not merely something that acts between objects within the universe. It is something that shapes the universe itself. The geometry of spacetime determines how the cosmos evolves, how structures grow, and how distances change over time. On the largest scales, gravity is not experienced as attraction toward a center. There is no center to fall toward. Instead, gravity governs the global relationships between regions of spacetime. It sets the stage on which cosmic history unfolds. The geometric role of gravity becomes even clearer when considering how structure forms in the universe. Galaxies did not appear fully formed. They emerged gradually from small variations in an otherwise nearly uniform early universe. These variations were tiny differences in density, barely detectable, yet gravity amplified them over immense spans of time. In the early universe, space-time geometry was close to flat. Matter and energy were distributed almost evenly. Where density was slightly higher, space-time curvature was slightly stronger. This difference altered the paths available to nearby matter. Over time, matter flowed along these paths, collecting into denser regions. Gravity did not pull matter together through empty space. Geometry guided matter into structures by shaping how motion unfolded. This process is visible today in the large-scale arrangement of galaxies. They are not scattered randomly. They form filaments, clusters, and vast voids. These patterns trace the underlying geometry shaped by gravity over billions of years. The structure is not imposed. It emerges naturally from spacetime, responding to matter, and matter responding to spacetime. Importantly, this behavior preserves the equivalence principle. On small scales within galaxies, objects follow local geodesics. Stars orbit galactic centers as they should. On larger scales, entire galaxies follow paths determined by the evolving geometry of the universe. The same principles apply everywhere. Only the scale changes. The expansion of the universe does not override gravity. It coexists with it. Where matter is dense, geometry curves inward, allowing bound structures to form. Where matter is sparse, expansion dominates, stretching distances over time. There is no conflict between attraction and expansion. Both are manifestations of the same geometric framework. This explains why the solar system does not expand, even though the universe does. Local spacetime geometry around massive objects supports stable geodesics. The expansion becomes relevant only where gravity is too weak to bind matter into structures. Geometry behaves differently at different scales, but it follows the same rules everywhere. Observations of the cosmic background radiation provide further confirmation. Tiny temperature variations correspond to slight differences in early spacetime curvature. These variations match predictions derived from the geometric description of gravity. The patterns observed today are fossil records of how geometry guided matter long before stars existed. Once again, gravity reveals itself not as a force acting on individual objects, but as a principle shaping relationships across space-time. The universe evolves because its geometry evolves. Matter moves because geometry tells it how. The story of cosmic structure is the story of curved space-time unfolding over time. The geometric description also clarifies why the universe does not behave the same way everywhere and at all times. Geometry is not fixed, it evolves. As the universe expands, the relative influence of different forms of energy changes. Matter, radiation, and other components contribute differently to space-time curvature as distances grow. The expansion history of the universe is therefore not arbitrary. It follows from how geometry responds to what the universe contains. This behavior is encoded in precise observational relationships. The rate at which galaxies recede depends on cosmic time. Distant galaxies reveal an earlier state of the universe, when geometry was denser and expansion proceeded differently. Light, traveling across billions of years, carries a record of how spacetime has changed along its path. These records are consistent across independent measurements, reinforcing the geometric interpretation. Gravity's role here is subtle. On the larger scales, it does not simply slow expansion or reverse it. It shapes how expansion proceeds in different eras. Early on, when matter and radiation were dense, curvature strongly influenced cosmic evolution. Later, as the universe expanded and thinned, geometry responded differently. The equations governing spacetime allow for these transitions without introducing new forces acting between galaxies. What matters for the present discussion is not the detailed contents of the universe, but the lesson they reinforce. Gravity, understood geometrically, governs both local motion and global evolution. There is no boundary where force-based intuition suddenly becomes valid again. The same framework describes falling objects, orbiting planets, black holes, and the expansion of the cosmos. When gravity is understood as geometry, its influence cannot be confined to stars, planets, or black holes alone. Geometry does not stop at the edge of a system. It extends everywhere. If spacetime can curve locally around mass and energy, then it must also possess a large-scale structure. The universe itself must have a geometry, and gravity must play a central role in shaping it. For much of human history, the universe was assumed to be static and unchanging on the largest scales. Stars appeared fixed. The sky seemed eternal. Space was treated as an infinite, empty backdrop in which matter was scattered. This assumption did not arise from evidence. It arose from familiarity. Nothing in daily experience suggested otherwise. As observations improved, this picture began to dissolve. Distant galaxies were found to be moving relative to one another. The farther away a galaxy was, the faster it appeared to recede. This motion was not random. It followed a precise pattern. Space itself was expanding. The geometric description of gravity has succeeded wherever it has been tested. It has explained falling objects, orbiting planets, the behavior of light, the ticking of clocks, the dynamics of black holes, and the large-scale evolution of the universe. Its predictions have been confirmed with extraordinary precision. Yet scientific success does not imply completeness. Every theory has boundaries, and gravity as geometry is no exception. The first sign of limitation appears where curvature becomes extreme. In certain solutions, space-time geometry evolves toward conditions where measured quantities cease to remain finite. Distances shrink to zero. Densities grow without bound. The mathematical description predicts points where curvature diverges. These regions are known as singularities, but the name should not be mistaken for an explanation. It is a label for breakdown. A singularity is not a place in spacetime in the usual sense. It is a signal that the equations describing spacetime have been pushed beyond their domain of validity. Physical quantities lose meaning. Time intervals cannot be defined. Paths cannot be extended. The theory does not describe what happens there, because it no longer can. These breakdowns appear in two contexts where gravity is strongest. One lies deep within black holes. The other lies at the earliest moments of cosmic history. In both cases, space-time curvature becomes so intense that the geometric framework predicts its own failure. The success of the theory elsewhere does not protect it from this limitation. Precision elsewhere only makes the failure more sharply defined. This distinction is crucial. The existence of singularities does not mean that nature contains infinite densities or points of infinite curvature. It means the theory describing geometry is incomplete in those regimes. Physics has encountered this situation before. Classical theories often fail when pushed beyond the scales at which they were constructed. Their breakdown signals the need for deeper principles. A second limitation emerges when gravity is compared with the quantum description of matter. All known non-gravitational interactions are described successfully by quantum field theory. These descriptions are built on probabilistic principles and operate within space-time, treated as a fixed background. Gravity, described geometrically, does not fit naturally into this framework. When attempts are made to apply quantum principles directly to space-time geometry, mathematical difficulties arise, calculations diverge, predictions lose meaning. The problem is not technical inconvenience. It reflects a deeper incompatibility between treating space-time as dynamic and treating it as a stage for quantum fields. No experiment has yet probed gravity at the scales where this conflict becomes unavoidable. The energies required are far beyond current capability. As a result, there is no experimental guidance about how geometry behaves under quantum conditions. Speculation exists, but speculation is not evidence. The geometric description remains silent where quantum effects should dominate. This silence is not a flaw, it is an honest boundary. The theory describes gravity accurately where experiments can test it. Where experiments cannot reach, the theory does not pretend to know more than it does. This restraint is a strength, not a weakness. Gravity as curved space-time therefore occupies a precise position. It is not an ultimate explanation. It is a remarkably successful description within a clearly defined domain. Its failures do not undermine its validity where it works. They define where new physics must eventually appear. The absence of experimental guidance at these extremes is not accidental. Gravity becomes dominant precisely where measurements are hardest. Inside black holes, no information escapes to distant observers. At the earliest moments of the universe, conditions existed far beyond anything that can be recreated. The regions where geometry fails are regions that remain observationally inaccessible. This creates a natural limit on what can be claimed. Any attempt to describe what happens beyond these boundaries must rely on assumptions that cannot yet be tested. Without experimental access, such descriptions remain provisional. Physics demands restraint here. Speculation may guide research, but it cannot replace evidence. One common misunderstanding is to treat singularities as physical objects. They are not. They are indicators that the mathematical framework has been pushed beyond its scope. The correct response is not to imagine infinite densities as real entities, but to recognize that the theory is signaling its own breakdown. The same caution applies to attempts to quantize space-time itself. Various mathematical frameworks have been proposed, each aiming to reconcile gravity with quantum principles. These approaches differ in assumptions and methods, but they share a common limitation. None has yet produced predictions that can be tested experimentally. Without such tests, none can claim empirical support. This does not diminish the geometric description. It clarifies its status. Gravity as curved space-time is not a hypothesis awaiting confirmation. It is a theory confirmed wherever confirmation is possible. Its failure at certain extremes does not negate its success elsewhere. It marks the frontier between known physics and open questions. There is also a conceptual limit that deserves careful attention. Geometry describes relationships. It tells how distances and times behave. It predicts motion, but it does not explain why space-time has the properties it does. It does not explain why geometry responds to mass and energy in precisely this way. These are deeper questions that lie beyond the theory's descriptive power. This distinction matters when interpreting what the theory claims. Gravity as geometry is a framework, not an ontology. It does not assert that geometry is the fundamental substance of reality. It states that geometry is the correct language for describing gravitational phenomena at accessible scales. Confusion arises when description is mistaken for explanation. The theory tells us how gravity behaves. It does not tell us why this description works at the deepest level. That question remains open. Recognizing this limit protects against overreach. It prevents turning a successful model into a metaphysical claim. Geometry explains observed behavior. It does not declare itself to be the ultimate constituent of nature. The strength of the geometric description lies precisely in its discipline. It matches observation. It avoids unnecessary speculation. It remains silent where evidence ends. In doing so, it preserves the integrity of what is known, while clearly marking what is not. If you want me to continue, say continue, and I will write Chapter 9, Part 3, in the same uninterrupted narration style. The final limitation emerges not from mathematics or experiment, but from interpretation. Once gravity is described successfully in geometric terms, it becomes tempting to conclude that gravity is geometry and nothing more. This step goes beyond what evidence allows. The theory does not demand such a conclusion. It does not forbid it either. It simply does not address it. Geometry in physics is a language. It encodes relationships between events, distances, and durations. It allows precise prediction. It does not specify what reality is made of. Treating geometry as an explanation rather than a description risks mistaking the map for the territory. The success of the geometric framework does not imply that space-time itself is the fundamental substance of the universe. This distinction becomes especially important at the boundaries where the theory fails. Near singularities and at quantum scales, geometry ceases to function as a reliable guide. Whatever replaces it may not resemble geometry at all. It may be emergent, it may be approximate, it may be replaced by concepts not yet imagined. Current evidence offers no guidance here. The phrase breakdown of geometry should be understood precisely. It does not mean that space-time tears or disappears. It means that the mathematical structures used to describe it lose predictive power. Physics has encountered similar situations before. Classical mechanics fails at atomic scales. Fluid dynamics fails at molecular scales. Each remains valid within its domain. Gravity as curved space-time occupies a similar position. It is exact where tested. It is silent where untested. It neither claims finality nor invites dismissal. It stands as the best description available, constrained tightly by observation and experiment. This careful positioning is essential to the question posed at the beginning. If gravity is geometry, is it therefore an illusion? The failures of the theory show why that question must be handled with care. Geometry may be a powerful, descriptive framework without being the underlying cause. Gravity may appear as geometry without being reducible to geometry at all scales. The evidence tells us how gravity behaves, not what gravity ultimately is. Geometry captures the behavior perfectly within known limits. Beyond those limits, the theory does not speculate. It stops. This restraint is not weakness, it is scientific integrity. It acknowledges that understanding is layered. What works at one scale may give way to deeper principles at another. Until those principles are revealed experimentally, geometry remains the correct and complete description where it applies, a carefully defined position. It is no longer a force acting across space. It is no longer an unexplained pull. It is described with extraordinary precision as the behavior of space-time geometry. This description has survived every experimental test placed before it. Yet description and explanation are not the same thing, and confusing the two risks overstating what physics has actually established. When gravity is expressed geometrically, nothing supernatural is being claimed. No hidden dimension is required. No philosophical assertion is made about the nature of reality. The theory states something precise and limited. The motion of matter and light, and the flow of time itself, behave exactly as if space-time has a geometry that responds to mass and energy. That statement is operational. It refers only to what can be measured. Calling gravity curved space-time does not answer why space-time behaves this way. It answers how gravitational phenomena appear and how they can be predicted. The equations specify relationships. They do not reveal underlying substance. They tell us how clocks compare, how paths curve, how signals propagate. They do not tell us what space-time is made of, or whether it is fundamental at all. This distinction matters because the word illusion is often misunderstood. An illusion in physics does not mean something unreal. It means something that arises from perspective. Centrifugal force appears in rotating frames even though no physical interaction produces it. It is not imaginary. It has measurable effects. But it is not fundamental. It emerges from description rather than mechanism. Gravity shares some of this character. When described from a constrained frame, it appears as a force. When described from a freely falling frame, it disappears locally. When described globally, it reappears as geometry. None of these descriptions are wrong. They are different ways of accounting for the same physical behavior. The illusion is not gravity itself. The illusion is that gravity must be a force. Geometry in this context is not an object. It is a bookkeeping system for relationships. It tells us which motions are natural and which require force. It tells us how time accumulates along different paths. It tells us how signals travel. The fact that this bookkeeping works universally is remarkable, but it does not elevate geometry to an ontological claim. Physics remains deliberately cautious here. It does not assert that spacetime curvature is the ultimate cause of gravity. It asserts that spacetime curvature is the correct description of gravity within all experimentally accessible regimes. That distinction preserves both the power and the humility of the theory. The question then becomes not whether gravity is real, but what kind of reality it possesses. Gravity produces measurable effects. Objects fall. Clocks disagree. Light bends. These are not illusions, they are observed facts. What shifts is the interpretation of their cause. The traditional image of a force pulling objects together turns out to be a convenient approximation rather than a fundamental mechanism. In this sense, gravity resembles other concepts that physics has refined over time. Temperature feels like a substance that flows from hot objects to cold ones, yet it is understood as a measure of microscopic motion. Pressure feels like a push exerted by matter, yet it emerges from countless collisions at scales too small to see. These quantities are real in their effects, but emergent in their explanation. Geometry may play a similar role for gravity. This possibility remains open. There is no experiment that can currently determine whether space-time geometry is fundamental or whether it emerges from deeper, non-geometric principles. What can be said with confidence is narrower and more precise. Every confirmed gravitational phenomenon is accounted for by geometry. No confirmed observation requires gravity to be something else. This careful phrasing matters. Physics advances by restricting claims to what evidence supports. Where evidence ends, claims stop. The temptation to declare gravity solved must be resisted. The geometric description closes one chapter of understanding, but it does not close the book. The word illusion therefore requires careful handling. Gravity is not an illusion in the sense of being fictitious or mistaken. Its effects are undeniable. What may be illusory is the idea that gravity is a force acting within a fixed stage of space and time. That picture dissolves when examined closely. What replaces it is not less real, but more subtle. From one perspective, gravity disappears in free fall. From another, it governs the shape of the universe. These perspectives do not contradict each other. They reveal different aspects of the same underlying behavior. Geometry provides a unifying language that connects them without contradiction. This language has limits. It breaks down where experiments cannot reach. It cannot yet be reconciled fully with quantum principles. It does not explain why space-time has the properties it does. These gaps are not failures of honesty. They are markers of where knowledge ends. In this light, asking whether gravity is an illusion becomes a question about interpretation rather than fact. Is geometry the thing itself, or is it the way gravity appears when described at macroscopic scales? Current evidence cannot decide. It only tells us that geometry works. The most disciplined position is therefore the most restrained one. Gravity is best described, not explained away, as the manifestation of space-time geometry. That description is exact wherever it has been tested. Whether it is fundamental or emergent remains unknown. The final position must remain grounded in what experiments actually justify. Gravity behaves exactly as if space-time has geometry. Objects in free fall follow geodesics. Clocks accumulate time differently depending on their paths. Light responds to curvature. Signals are delayed. Distances change. These statements are not interpretations layered onto data. They are direct summaries of measurement. What has not been established is whether geometry is the underlying cause of these effects or the most effective description of them. Physics does not currently possess an experiment that can distinguish between these possibilities. Any claim that space-time itself is fundamental would exceed the evidence. Any claim that geometry is merely a convenient fiction would also exceed the evidence. The correct stance lies between these extremes. This is where the word illusion must be handled with precision. In physics, an illusion often refers to a description that depends on perspective, rather than a non-existent phenomenon. Weight is felt when motion is constrained. It vanishes in free fall. The sensation is real, but its cause is not a force acting downward. The illusion is the interpretation, not the experience. Gravity fits this pattern. The experience of weight suggests a pull. The deeper description reveals constraint. The force appears in one frame and disappears in another. Geometry remains consistent across all frames. What changes is how motion is described. The illusion is not gravity. The illusion is force. This distinction preserves everything that has been learned without adding anything that has not been tested. It allows gravity to be both real and non-fundamental in the traditional sense. It allows geometry to be both indispensable and possibly emergent. It respects the limits of knowledge without retreating into uncertainty. Physics has reached this position before. Concepts once treated as fundamental were later understood as effective descriptions, yet those descriptions remained valid within their domains. Gravity as geometry may occupy a similar place. It may be the correct macroscopic description of deeper processes not yet accessible to experiment. Until such processes are observed, the geometric framework stands unchallenged. It predicts every confirmed gravitational phenomenon. It remains internally consistent. It integrates gravity with the structure of space and time in a way no force-based description ever could. The most accurate statement that can be made today is therefore also the most cautious. Gravity is not proven to be an illusion. It is not proven to be fundamental. It is proven to behave exactly like space-time geometry within all experimentally tested regimes. That conclusion is not disappointing. It is powerful. It shows how far evidence alone can take understanding without speculation. It reveals a universe in which motion, time, and structure are inseparably linked. And it leaves open the possibility that deeper layers of reality remain to be discovered, waiting for experiments capable of reaching them. Gravity has carried us from falling stones to the shape of the universe itself. Along the way, familiar ideas were stripped away, not because they were wrong, but because they were incomplete. Force gave way to motion. Motion gave way to geometry. Geometry gave way to questions it cannot answer on its own. At this final edge, physics does not collapse into mystery. It becomes precise about what it knows, and equally precise about what it does not. Every confirmed observation of gravity fits within the geometric description. This fact cannot be overstated. No experiment has ever required gravity to behave differently from curved space-time. No measurement has revealed a hidden force acting beneath geometry. No deviation has appeared that demands a competing framework. Within its tested domain, the description is complete. Yet completion within a domain is not finality. Physics does not grant permanence to any description merely because it works. It asks a different question. What is the domain of validity, and what happens when that domain is exceeded? For gravity, the boundary is clear. It lies where space-time curvature becomes extreme and where quantum behavior cannot be ignored. At those boundaries, geometry does not offer answers. It stops. The equations lose predictive power, not because they are wrong, but because they were never meant to operate there. This silence is not a flaw. It is an honest admission of scope. This honesty matters when interpreting what gravity is. The geometric description tells us how gravitational phenomena behave. It does not tell us why spacetime responds to mass and energy in this way. It does not tell us whether spacetime itself is fundamental or whether it arises from deeper processes. These questions are not avoided. They are simply unanswered. Physics has learned to distinguish between explanation and description. An explanation reveals underlying mechanisms. A description captures patterns with precision. Gravity, at present, belongs firmly in the second category. It is described exactly. It is not yet explained at the deepest level. This distinction prevents a common misunderstanding. Saying that gravity is geometry does not mean that geometry is the ultimate substance of reality. Geometry is a framework for organizing measurement. It tells us how to compare clocks, how to track motion, how to predict outcomes. It does not claim to be the final layer beneath all phenomena. Many successful physical theories share this character. Thermodynamics describes heat and work without revealing the atomic details beneath them. Fluid dynamics describes flow without tracking individual molecules. These descriptions are not illusions. They are accurate at their scale. They become incomplete only when pushed beyond it. Gravity may belong to this class. Geometry may be the correct macroscopic language for a deeper microscopic structure not yet accessible. Or geometry may be fundamental in a way unlike anything else. Current evidence cannot decide between these possibilities. Any claim in either direction would exceed what experiments justify. This restraint is not weakness. It is the strength of physics. By refusing to speculate beyond evidence, it preserves clarity. Gravity, as we can measure it, behaves exactly like spacetime geometry. That statement is as strong as it is limited. The temptation to go further is understandable. Humans seek closure, but nature does not promise it. Knowledge advances not by declaring final answers, but by tightening the boundary between what is known and what remains open. Gravity has now been pushed to that boundary. This is not an ending in the sense of completion. It is an ending in the sense of arrival. We have arrived at the most accurate statement evidence allows us to make about gravity today. Beyond this point, the path forward belongs not to interpretation, but to experiment. The boundary where geometry stops is not marked by confusion, but by discipline. It is the place where equations no longer return finite answers and where predictions can no longer be tested. Physics does not cross this boundary by imagination alone. It waits. That waiting is not passive. It is structured by everything already known. One of the most important lessons gravity has taught is that intuition is unreliable at fundamental scales. The idea that forces pull objects through space felt obvious for centuries. It was wrong in its deepest sense, yet extraordinarily effective within its limits. Geometry replaced it not because geometry was more intuitive, but because it was unavoidable. Evidence demanded it. This pattern matters for what comes next. Whatever lies beneath geometry will not resemble everyday concepts. It will not feel natural. It will likely contradict intuition just as strongly as curved space-time once did. Expecting comfort from future explanations is a mistake history warns against. What can be said with confidence is that any deeper description must reproduce geometry where geometry works. Just as geometry reproduces Newtonian gravity, where curvature is weak, any future theory must reproduce curved spacetime wherever experiments confirm it. This requirement is not optional. It is enforced by data. This constraint sharply limits speculation. Many imagined explanations for gravity fail not because they are uncreative, but because they cannot recover the precise geometric behavior already measured. Precision is unforgiving. A theory does not get credit for being conceptually satisfying. It must be numerically exact. The success of geometry also reshapes how questions are framed. Instead of asking what force pulls objects together, physics now asks what determines spacetime structure. Instead of asking why objects accelerate, It asks why geodesics take the form they do. These questions are not philosophical, they are operational. They are about measurable relationships. At present, no experiment has detected granularity, discreteness, or underlying constituents of spacetime itself. Spacetime appears smooth down to the smallest scales probed. Geometry works continuously. Whether this smoothness persists indefinitely or breaks down at scales beyond reach remains unknown. But unknown does not mean arbitrary. Gravity's resistance to quantization is often misinterpreted. It is not that geometry refuses to be quantized. It is that current methods fail to do so without losing predictive power. This failure does not imply impossibility. It implies incompleteness of current tools. History suggests such impasses precede major conceptual shifts. The same was true before quantum mechanics. Classical physics could not explain atomic stability, radiation spectra, or specific heat. The solution was not to abandon classical physics where it worked, but to recognize its limits and build something deeper that reduced to it in the appropriate regime. Gravity may be waiting for a similar transition. Importantly, nothing observed so far suggests that gravity behaves differently from geometry at accessible scales. There is no anomaly pointing beyond it. There is no crack to widen. This absence of contradiction is itself informative. It means that whatever lies deeper must be subtle. It must hide behind geometry rather than replace it outright. This leads to a crucial epistemic position. Geometry is not a placeholder awaiting correction. It is the correct description of gravitational phenomena within all tested regimes. Treating it as provisional in the same sense as an untested hypothesis misunderstands its status. It is established fact at macroscopic scales. The openness lies not in whether geometry works, but in why it works so universally. Why mass and energy curve spacetime rather than acting through some other mechanism is not answered by geometry itself. It is simply encoded. That encoding is exact. The explanation is absent. Recognizing this absence is not an admission of ignorance. It is an accurate statement of the boundary between description and explanation. Physics has always progressed by respecting that boundary. When it is crossed prematurely, error follows. Gravity has therefore reached a rare position in science. It is both deeply understood and fundamentally mysterious. Its behavior is mapped with precision. Its ultimate origin remains unknown. These two statements are not contradictory. They are complementary. The final lesson gravity offers is not about space-time alone, but about how knowledge itself advances. Every step in the story of gravity followed the same pattern. Observation came first, description followed, explanation lagged behind. At no point did nature reveal its structure because it was asked politely or imagined creatively. It revealed itself only when measurements forced a change in language. Gravity was first known as weight, then as motion, then as force, then as geometry. Each transition did not erase what came before. It absorbed it. Falling stones did not stop falling when geometry appeared. Orbits did not dissolve. The old descriptions remained valid where their assumptions held. What changed was not reality, but understanding. This layered structure of knowledge is essential. It prevents the mistake of assuming that deeper means truer in every context. Newtonian gravity is not false when an apple falls. It is incomplete when precision increases. Geometry is not false where quantum effects may one day dominate. It is complete where it has been tested. Truth in physics is contextual, bounded by domain. This is why the question of illusion must be handled with care. In everyday language, an illusion implies deception. In physics, it implies perspective. Something appears real from one frame and disappears in another. Both descriptions are correct. Neither has privileged access to reality on its own. Weight is real when standing on the ground. It vanishes in free fall. Neither experience is mistaken. The force is not fundamental, but the sensation is real. Gravity fits this pattern precisely. The pull is frame-dependent. The geometry is frame-independent. What persists across all descriptions is the pattern of motion itself. Geometry captures that pattern without remainder. It does not require additional assumptions. It does not invoke unseen agents. It does not rely on metaphors. It encodes what clocks measure, what rulers measure, what paths objects follow. That is its power. At the same time, geometry refuses to answer questions it is not equipped to answer. It does not say whether spacetime is made of something. It does not say whether curvature emerges from deeper interactions. It does not say whether geometry is fundamental or approximate. These silences are not gaps in rigor. They are boundaries enforced by evidence. This balance between precision and restraint is the defining strength of modern physics. Gravity as geometry exemplifies it perfectly. Where evidence speaks, the theory speaks clearly. Where evidence is silent, the theory remains silent as well. It is tempting to want more, to want gravity reduced to particles, or spacetime replaced by something smaller, or geometry declared an illusion in a stronger sense. But temptation is not justification. Until an experiment demands such changes, geometry remains the final word gravity allows us to say. This does not mean progress has stopped. It means progress is waiting for new tools, new measurements, new access to regimes where current descriptions fail. History suggests such moments arrive unexpectedly. When they do, gravity will change again, not because geometry was wrong, but because it was incomplete. Until that moment, the most accurate statement remains simple and constrained. Gravity behaves exactly as curved spacetime within all experimentally tested regimes. This behavior is not an illusion. The interpretation of gravity as a force is. Geometry is not proven to be fundamental. It is proven to be sufficient. That is not a disappointment. It is an achievement. It means that nature, when questioned carefully, responds with consistency rather than contradiction. It means that understanding can deepen without discarding what is known. It means that mystery and precision can coexist. Gravity began as a familiar pull and ended as the shape of the universe itself. Along the way, it taught a deeper lesson. Reality does not owe us intuitive explanations. It owes us patterns. When those patterns are followed without overreach, understanding advances as far as evidence allows and no further.